Now can you see the screen? Okay, Lay? Okay, tell me.
Yes, sir. Yes.
Okay, good.
Yes,
So
sir.
yeah, good. Okay, yeah. So Lagrange theorem. This is what we did, and disjoint union of the cosets. This has an implication, particularly two, which I personally feel that these are, I mean, these three which are very important. That we know that order of each element would be only the factors of this mod G. Possible subgroups of G is what we can find out. This is very important consequence. That does not mean that that subgroup has to exist, but at least we can narrow down your numbers. And in the case of prime, of course, this number narrows down to a single one, that it will always be a cyclic group. We know cyclic group is always an abelian group. So that way for the cyclic group, yeah, for the prime, it's always going to be cyclic. Question comes another important concept coming out of the cosets. Normal subgroup, the definition being rather simple. Left coset is equal to right coset, and we define that subgroup as the normal subgroup. Okay, we have an example. We also come up with this point that the abelian subgroups of a group, they are always going to be normal. And then we come up with something further, that once you have a normal subgroup, then you can construct cosets, all possible distinct cosets, and then you can define your coset multiplication in such a way that these cosets will themselves form a group. And the formation of this group, which is out of the cosets of a normal subgroup, that group is called a factor or a quotient subgroup, H of G. Yeah. So, and the order of this quotient subgroup, that also comes naturally from the order of the group and the normal subgroup. Now, this is what we are doing, and I will continue with this. So, classes or equivalence classes, or I should even write down conjugacy classes. These classes basically are going to give you another way of defining a normal subgroup, and we are into that. The idea is basically coming from the point that you understand that we have this H inverse is equal to H. Yeah. So first we define what is a conjugate element in a group. Conjugate elements are those elements which are related with each other by this relation, which is G2 is equal to G inverse G1G, or G1 is equal to G2 G inverse. So that's the relation. If it obeys, then we say that the two elements are conjugate elements. We further said that conjugate elements also, of course, have certain properties. The simplest one, another one which I extended, was if G1 is conjugate of G2 and G2 is conjugate of G3, then G1 is conjugate of G3. The important thing which I wrote towards the end, for which we are going to have an example, group can be divided into sets such that all elements of a set are conjugate elements of each other, and no two elements belonging to different sets will be conjugate. Okay, so this is what we would like to do by having an example. So let's just take the example from this D3 group, and this group has this element ERR square, L1, L2, L3, and I requested all of you to just get the multiplication table ready with you guys. That is what I am going to rely on when I'm going to go through this concept. So first element is E. So let's just see what are the conjugate elements of E. So we will have to basically consider all other elements and take what we defined as our definition. So first, R inverse ER. What is the result? R inverse ER. E is an identity element.
E, sir.
E, yeah,
E.
right. E. I mean, there cannot be anything else, because E, that means that this guy can be written as R inverse R, which will give you E by definition of the group. And you can take any element. You take L2 inverse E L2. What will this guy be? because E times L2 will always be L2, L2 inverse L2 will be E. So that means what? That the element which is conjugate of E is the element itself. Since we are going to divide our whole group into sets, so first set will be a simple one. This set or the class, which I will call it, will contain only one element, and that element is E. Because if you do these relations, R inverse ER, R square inverse ER square, so on and so forth, you will get only one result, which is E. So E is conjugate of itself. That is what the meaning is. Okay, let's do something for a non-trivial one. Let's just take R, second element. So this was the first element, it was simple. Now let's, of course, I can take E inverse or E, and what will be the result?
R.
R. So that means that, of course, I mean, this guy, this class will have this element R. Now let's just do the next one. R inverse. Okay, just try to do this guy. What is
R.
the inverse of R? What is this guy? R inverse. And that is why I require this scalar multiplication. Okay, this is R square, then this is R, then this is R. So what will be this result?
R square into R is E, sir, and E into R is E. Oh, sorry, R.
So R, so basically what you say is that R4 has come where R cube is equal to E. So you know that R cube times R will only be R. Good. So let's just continue. So R square inverse R square. What will be this element? So what is the inverse of R square?
R.
R. So what will be R into R square then?
So R.
Again R.
R.
So you are not going to get something new. So R is there already, you have found. Let's just do now L1 inverse R L1. What is L1 inverse? What is L1 inverse? First.
L1.
L1, sir.
Okay, so
L1,
this
sir.
is L1 R L1, and ordering does not matter whether you can do R L1 and then multiplied by L1 or L1 R and then multiplied by L1. It is up to you. So let's just do it this way. R into L1. What is the result?
L2.
R into L1 is L2.
Yes, sir.
Okay. And then what will be the result of L1 into L2?
R3.
R,
R
R
square.
square, sir.
R squares. Okay, now you have got one new element in this class. So in class number 2, you have R square. Okay, now of course, next thing is supposed to be L2 inverse R L2. What will be this guy? So again, L2 inverse will be L2 R L2.
R square total.
R square again. Okay, in that case, L3 inverse R L3. L3 inverse is L3. So L3 times R times L3. So those of you who are not doing it because they do not have the Cayley multiplication table ready, they of course require more time to do it. And that is why Cayley multiplication table before coming up with classes is very useful. Yeah, go ahead.
R square, sir.
R square. Okay, good. In fact, if you see that R and R square, that's class number 2, And this will tell me that I do not need to now find separate class for R square. Although for the sake of completion, you can do the same exercise now for the next one, which is R square, but you do not need to, as R square already belongs to a class in which R is already there. So in some sense, that if you find out that there exists an element like R square in this case, which is part of this class because they are conjugate of each other, then you do not need to separately find out the class for R square. It will always form a class R square R and nothing else. That's the interesting thing. But we are not yet exhausted. अभी तो हम लोगों को class elements बचे हैं. So now we'll have to do it for L1, L2 and L3. So let me just see that if you can come up with something pretty quickly for L1, L2, L3. How are you going to go ahead with it? You are going to go ahead with it exactly in the manner in which we are doing it. So first element will be okay, inverse L1. Which will be L1. So let's just go ahead with the next one. So L2 inverse L1 L2. What will be this? So L2 inverse is L2 itself. So L2 composition L1 is L2.
L3, sir.
So L3 in this class you have already find one more element which is L3, and you will figure out that there exists another one just in the manner in which we have done it. So what you will get in essence, so I will not ask you to go ahead with it, but do it as the homework, that this D3E is divided into three classes. Now look into the classes which we have made. These three classes come here. So I call them C1, C2, C3, although C's are also reserved for C2 new. I mean, some of the people don't call dihedral group, particularly if they are not into crystallography, and they use some notation C2 new. Anyway, for us, let me just specifically write these are the classes. There exist three classes in this case. What is the way we have come up with these classes? We have come up with these three classes on the basis of the conjugacy. Conjugacy, which was defined as G inverse G1G is equal to G2. All elements of a single class are nothing but the conjugate of each other. Once an element is conjugate of another one, or is in, let's say, in class C2, same element will not come in any other class, say C1 or C3. So that's interesting. E, identity element will always make a class of its own. So let me write down. Identity, it will always be in a class of its own. Okay. And then what was written on the previous page? No two classes contain any same or similar element. Okay, no two classes contain same or similar elements. That means R, if it is in class C2, it cannot be in C3. L2, if it is in C3, it cannot be this. Now I said that we can form normal subgroup out of these classes. This was the starting point actually. So what happens, that here comes the interesting development, that if I want to make now subgroups, forget about normal subgroups, then these subgroups will always, so first point, always contain complete classes. Yeah. So what in essence I am saying, that if I want to make a subgroup, then it will be E R square as either C1, C2, or it will be E L1, L2, L3. But here is a catch. The catch is E L1 makes a subgroup. So there looks like that there is something fishy. It's not something fishy. It is that normal subgroups always contain complete classes is the complete definition. That in case if you are going to form normal subgroups out of the classes, then the only possibility which exists that those subgroups will always contain complete classes, and surely it will have to have the identity element added to that class. Without identity element, you cannot even form a subgroup. Yeah. So this ERR square and this EL1, L2, L3, that's the only possibility for the normal subgroups, and there exists no other possibility for the normal subgroups. So this is something interesting about the normal subgroups, which thus far we were studying from the point of view of cosets, that the left coset is equal to right coset. But once we understood the structure, what was the structure? Once we understood the structure that XH is equal to HX implies that we can have X inverse kind of a structure or X inverse HX kind of structure. We try to utilize this fact by saying that we will divide the whole group into equivalent or the conjugacy classes. What is meant by the classes? Classes are those sets. Remember, they are not subgroups because E is a class in itself, and hence E cannot be in any of the other set. And if E cannot be there in any of the other set, that means that none of those sets can form the groups in themselves. So none of the classes will form the subgroup or group other than this one class, which is E class. Yeah. But anyway, the definition of the conjugacy is G1, G inverse G1 G is equal to G2. This is what we used to form the conjugacy classes, and those conjugacy classes ultimately it is contained in one single sentence that group can be divided into, now I can use again the same word, disjoint sets, such that all elements of a set are conjugate to each other. So at this point, I will take a pause and I will tell you that what we have done, we have started by saying that groups are there, and then there exists structure called subgroup. Now, from the subgroup, I can take these cosets, and left equal to right gives me normal subgroup, and from these normal subgroup I can also make factor groups. So remember, this is n, this is okay, I write G colon n, and this was H, and this is G. I can take another route now. I can take a route what is called the route of the classes. Here I did not form any subgroup to begin with. If you look into it, I did not. I just take each element and I keep on finding out G inverse G1 G for each of the element. And there we get the idea of the classes C1, C2, C3, where let's say this C1 is this guy E. So this gives me another idea of these normal subgroup, which is, let me say as the normal one. Okay, I have written, sorry, normal subgroup. In this case, what we are saying that normal subgroups will always be those subgroups which will contain E and the complete classes. It doesn't mean all the complete classes, if you add them, then they will form group. So C2, C3, if they are added together, it is not going to form group. Yeah, but C1 if added to that, that is going to form group. The normal subgroups you can figure out also from the classes. So groups, disjoint union of cosets. So this is one disjoint union, or otherwise classes, which is nothing but another disjoint union. So this is what we have done up to now, that we have tried to understand the properties of the groups by dividing into disjoint union and came up with the concepts of normal subgroups and the factor groups. So at this point, I will take a pause and I will let you ask questions.
Sir, classes do not need to form satisfy the categories of the groups, right?
Yeah, they are the sets, right? That is why I said sets, right?
Okay.
Yeah, so individual R is square, that's a set. So let's just go back and again read that. I wrote sets and then I underline it and then I put apostrophe. That you remember, it is not a subgroup in itself. Classes are just classes. But very interesting one. They are disjoint union, just like cosets, they are disjoint union. And you can form subgroups out of it. So those are the two
E
interesting.
placed with classes forms normal subgroup.
Say it again.
E placed with classes form normal subgroup.
Right. Yeah, but at the same time, I mean, please keep on checking. Remember, the way we have come up with the idea of the classes is such that it will ensure that somehow this G inverse G1 G has this interesting property. So this is actually the homework question which I want to give to you. In fact, your question leads me to give you a question which actually I wanted to give. Show that X inverse HX forms a subgroup. This one. So the equivalence classes which we are making, basically, I am now trying to ask it in terms of a concrete question, that you show that X inverse HX forms a subgroup, of course, where X belongs to G and X does not belong to H. Okay. So show that. That way you will understand that this guy X inverse HX, which I said as the similarity transformation, has this interesting structure. I mean, I told you from the left coset equal to right coset side already, but try to do this problem. All you need to do is to check if identity is there in this one, if inverses are there, if closure is there. Associativity, okay, of course you will check it, but it will be automatically done, taken care of. But please do that. And as a homework, in case if you face any problem, just come back to me. I mean, I'll help you out. But this is the interesting reason that we came up with the idea of the classes, that we know that this X inverse HX kind of structure is going to make a subgroup. So can we make somehow use these to form a normal subgroup? That was the idea. And that's the idea which we have basically implemented. Okay, since we are into concepts, by the way, those of you who have done your discipline specific elective DSE, I guess they already know this, because I have to reach up to representation theory, and till that they may have already been knowing these things. Still, I am not leaving that. I am basically trying to do everything here. Now, this is something interesting. Direct product of groups. It is also thought of as enlarging a group. Thus far, we were seeing that, okay, I can fragment my group into smaller subgroups, so on and so forth. Can I think about enlarging a group? So let me just give you an example. So let me take a group G1, yeah, under some rule of composition, and this has only two elements, so E and A. Can somebody tell me what can be the structure of this guy, two element group? The only one structure which is possible is
1 and minus 1.
yeah, but that is only one implementation, right? That you have used that for complex root. What is the only possible group theoretic structure for two elements? That group has to be
cyclic abelian.
Cyclic abelian. Cyclic is yeah. So that means the only possibility is A square equal to E. You can, of course, we did it from the Kelly's multiplication theorem, but this is the E is already A square in that. Let's say there exists another one, G2. Yeah, another composition. And say, let's say this contains E times B, or maybe same composition, let's say for the time being, simpler one. And for this guy, the only possibility is
So B square equals to E.
B square equal to E. There cannot be any other one, right? So now think about doing something like this. G1 dot, which is my one group, I multiplied by another group, this G2 dot, where I am saying that B is not equal to A. If B is equal to A, then it is not no point doing that. If B is not equal to A, then what will be the element of this group? Can somebody tell me? So I am going to take all possible products. This guy, this guy. So first E to E, what it will give?
E.
E. E with B.
A, B, A, B.
Okay, A, B, A, B. And consider that the two groups are normal, the subgroups. By the way, is G1 dot a normal subgroup or G2 dot is a normal? I mean, in terms of the group structure, you will have to now think about it. Since it's not a subgroup, how will we define normal? So we cannot. So can you check whether it's an abelian group, EA and EB? Can you check individually? Or do you need
Yes,
to?
sir, it is actually.
I mean, we already know it is a
We don't need to.
Yeah, it is cyclic. Remember, cyclic groups are by default. You said cyclic abelian because that is how I said that. But these are abelian. However, there is one additional structure which I am asking now, that AB is equal to BA. That element of group G1 is abelian with element of group G2. So if I have this as one of the condition, and also I have a condition that identity element is the only common element between the two. So out of E and A, there is only one element which is common, which is in the two groups, this is the identity element. Now look into what we have made out of it. We have made E, A, B, AB. We already know A square is equal to E. We already know B square is equal to E. That was by definition of the two groups, of course. And we already know that AB is equal to BA. So can you now give me AB square?
E, sir, E.
E.
It will be E.
E. So now you will see something interesting. I have a group of 2, let's say I am calling it Z2, another group of order 2, I am taking a product and I am getting a larger group Z4. This is a group of 4 elements. Each of the element is having, see, A square is equal to E, B square is equal to E, and AB square is equal to E. And this AB is equal to C. If you remember that when I asked you to find out the group structure for 4 element group, this was one of the groups which you formed. I wrote at that time Z4 is nothing but Z2 into Z2. At that time I said I am keeping it reserved, and now I am going to open it. What I am opening here is that we can think about enlarging a group by taking the direct product of the groups. Now, direct product of the groups is possible if the identity element is the only common element between the two groups and the elements AB is equal to BA. That elements are commutative in nature. Whenever these two conditions are met, you will find out that you can enlarge the group in a very simple manner. In fact, I will now remind you that Z4 had only two possible structures. One structure was 1G, G square, G cube, which means that this one is nothing but G4. So this, let me write it as identity. And the other possible structure was E, A, B, C, where A square is equal to E, B square is equal to E, C is equal to AB is equal to B, such that C square is equal to. So these were the only two structure. One was simple to make because that was, remember, that is a cyclic structure. You can always make cyclic structure for any group. But then another one which you were thinking, okay, how to get, what kind of structure you can get, this guy turns out to be nothing but Z2 cross Z2. And how can we know that we have understood it? So maybe classwork. Let's just do it as a classwork. So let me just give you two element group EA and another Z3 EBB square, such that every element is commutative, 1, and 2, identity is commutative anyway. E is the only common element. Only common element, which means that A cannot be equal to B and A cannot be equal to B square. Can you enlarge the group Z2 cross Z3 and give me the result? What will be the elements of the group?
E, B,
So,
B
okay, let me write
square.
E, A, B, B square. That will come naturally, okay.
AB, AB square.
AB, AB square. How many elements you have found?
6.
6 elements you have formed. And since they are commutative, so I do not need to form anything other than that, right? So now this group EAB, B square, AB, AB square, you somehow now know that this is Z6 group in our language, and you also know certain properties which are there. What is the property? 1, A square is equal to E. Another property?
B square is equal to E.
No, not B square, because B square was there.
B cube.
B
B
cube.
cube is equal to unity, and AB is equal to BA. You can figure out whether this group is isomorphic to, and not isomorphic. You can just figure out the multiplication table. Okay, forget about anything. Check the multiplication table, since we haven't yet reached to the isomorphism. So the idea is the direct product of the groups, very interesting concept. The concept wise, you can now think about enlarging groups, and you can form larger order group just by from the smaller ones. Here the conditions which we are using, the ones where the abelian structure of the group is there for both the groups. There is only one structure, there is only one element E identity which is common between the two of them. If those are the conditions which are met, then you will. In fact, direct product of the group does far more than that, but I am just going to go ahead only up to this point. Okay, because direct product of the group is a very good concept. You can always think about taking two groups, multiply them, and try to enlarge your existing group to the larger set. Questions?
So,
Yes.
सर जब हम इसमें ऑपरेशन लगाते हैं तो हम लेफ्ट से लगाते हैं सर या राइट से?
अगर इस केस में आप लगाओगे, क्योंकि ये तो हमने क्या कहा, देखो अभी तक के जितने भी तुम्हारे ग्रुप है, ये साइक्लिक है, एबिलियन है, राइट? फर्स्ट वन Z2, Z3 भी साइक्लिक है, एबिलियन है. तो तुम्हें ऑलरेडी पता है कि इन केस में तो स्ट्रक्चर लेफ्ट से लगाओ और राइट से लगाओ, कोई फर्क ही नहीं पड़ेगा, राइट?
सर जो आपने D3 वाला एग्जांपल कराया था,
ओके, हाँ, ओके, दैट द वे आई डिफाइंड दैट, लेट मी जस्ट टेल यू. मैंने हमेशा जो आपको कराया है उसमें मैंने हमेशा कहा है सबसे पहला ऑपरेशन आर स्क्वायर लगता है. लेट्स से R1, not R1, alpha 1, alpha 2, alpha 3. It is an operation which is going to be based on A, B and C, which was our identity triangle. So first you are going to put alpha 3, right? Then you are going to put on this alpha 3, alpha 2. That means this one, and then you are going to make alpha 1. But if you remember that the composition is such that it does not matter whether you apply these two operations first or you apply alpha 1 dot alpha 2 first and then you take alpha 3. So that associative property holds true, but otherwise for this composition I always said apply alpha 3 as the first one, alpha 2 as the next one, alpha 1 as the last one. So your Cayley multiplication table, what you must have made, should be according to this. Have I answered your question?
Yes, sir.
Okay, good. Yeah, this is something which I mentioned. This is very important for operations, particularly for operations like this, that if you have an object on which you are applying, yeah, so then you will have to think about how you are applying this on some object. So you start with the original object and you start applying operations on that. Once you are comfortable with that, you will figure out that you do not even need to think about the original object, because the association law will allow you to take care of this left and the right hand side operation. I mean, alpha 1, alpha 2, alpha 3 in any order to be done, as long as you do not change the order. I mean, the brackets, of course, you can place associative nature, but you cannot change alpha 2 dot alpha 1 in non-commutative groups. So alpha only in those abelian groups it is always true. In non-abelian groups, alpha 1 dot alpha 2 is not going to give you alpha 2 dot alpha 1. That is the case with this D3 group. That D3 group in general is a non-abelian group. So you will not find for all the elements alpha 1 dot alpha 2 is equal to alpha 2 dot alpha 1. Even though for some of the elements it is true, but for other elements it's not. Okay, any other?
इस Z4 is a special group ना, इसका कुछ नाम भी है शायद special case.
No, I mean I told you the group names of the Weir group. That is the German name which is given to this kind of a structure, Z2 into Z2 kind of a structure, which is coming out of Z4. But let me just tell you, I mean, since we've asked, by the way, the word Z I have kept from the modular arithmetic. And just to tell you what it is, if I have mod 2, what is the meaning of mod 2 if I have a number here? Can somebody tell me? Just want to know if somebody knows it. No. So it is about what is the remainder which is left. Okay, remainder is remainder which is left, bad mod. So if I put n mod 2, then I am interested in figuring out what is the remainder which is left after dividing it by 2. So let's just see 0 mod 2. What is the result? 0. 1 mod 2. What is the result? 1. 2 mod 2. Remainder. Oh, you said something. 0. 3 mod 2.
1.
1. 4 mod 2.
0.
0. That means what? That means that you are mapping all the even elements to 0 and all the odd elements to 1 in this integer. Yeah. So think about it. Okay, I am again going into something here. So think about it. That means that I am now talking about a group which is nothing but something mod 2. I am not saying that how it forms a group, but it does form a group under simple addition. You will find out 0, 1. So in this case, 0 mod 2 plus 0 mod 2 is equal to 0 mod 2. You will find out interesting will be 1 mod 2 plus 1 mod 2 is equal to what? So 1 mod 2 turned out to be 1.
1.
Plus 1 mod 2 turned out to be 1 plus 1. So this is equal to
2.
Yeah, 2 when divided by mod 2 will be 0. So the result is that 0 mod 2. So in fact, you will see that this 0, 1, 0, 1 is going to make this interesting group table. And that is for Z2 whenever you are divided by 2. And then you can think about Z3, any number mod 3, not any number, integer mod 3. And that will have 3 elements. Z4, integer mod 4. This will have 4 elements. So it is actually in group theoretic language, it is that they have for all the countably in finite groups, we have this possibility of going with the modular arithmetic, and it can be shown that each group is isomorphic to some group. Yeah. So whenever I am writing Z2, I am basically writing a notation. So it is only mainly about the notation. What I wanted to say, that the notation is coming out of the modular arithmetic. By the way, the one place where you are using your modular arithmetic very regularly is your clock, which is there on the wall. If you just put 12 instead of 12, you would use the number 0. And I ask you, what is the time when it is 14 hours? So what will you say? 14 hours. What time it is?
2 p.m.
2 p.m.
2
What
p.m.
is the time when I ask you that it was 6 p.m. 6 hours after 9 p.m. After 9. So whatever 9 is, your watch is there. And I say in the clock, if I add 6 hours to that, at what place your clock will reach?
3 a.m.
It will be 3,
3.
right?
3 a.m.
Yeah, I mean your AM and PM doesn't get reflected in the clock. That is what your idea of AM and PM is. That you look at outside and you know, okay, it is AM or PM. But please understand that on the clock there is no way it is written AM or PM. Yeah, I mean there is nothing which is written there. It has only 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 which is written. And after that, whenever it is 2, you say, okay, it is 2 PM, but it is number is at 2. Somehow you already have this arithmetic in your mind that it is mod 12 arithmetic which I am using, which is 0 mod 12 is 0 up to 11 mod 12 which is 11, and as soon as you reach to 12 mod 12 you will say, okay, it is 0 hours again, and then you will again counting it like that. Then 13 mod 12, okay, this is 1 because 13 divided by 12 remainder is 1. 14 mod 12, it is 2. So your clocks are based on modular arithmetic, which was invented by these the famous, I mean the same Gauss who came up with this Gaussian, I mean distribution. Yeah, so that's what the modular arithmetic is. And since we can always use modular arithmetic to form groups, and it can be shown that any order of element group can be isomorphic to one of these. So this is the reason why I keep on using these Z2s, Z3s, Z4s, so on and so forth. I do not need to explicitly write down the group name, to be honest. I can just say that these are groups. So G2 into G3. It is okay. I have a habit of writing my Z2, Z3 because I know that this happens. For you, it is okay. I just gave some name. And now I have told you how I came up with these names. It is coming out from the modular arithmetic. Okay. Okay. Did it make sense? I mean, to few of you, if not to all.
Yes, sir.
Great. Thanks.
Yes, sir.
Okay. Okay. Now coming up with a very interesting concept. I mean, none of the concept was not interesting before this, but this concept is used just like anything. Homomorphism and isomorphism, I will just restrict myself to these two. I mean, there are words beyond that, but I will not invoke those. Again, not to confuse you further, group theory, remember, is an abstract algebra. So what is about the homomorphism? I will start with this and then I will come to isomorphism. Yeah, generally people go opposite, but I will go in the homomorphism first and then isomorphism. Now, what am I talking about now? I am talking about, let's say, two groups. So one is G, another is G prime. And let's say operation in this group is star, operation in this group is composition. Yeah. So I am now talking about a mapping basically. A mapping which will take me from one group to another group. So as soon as you hear the word homomorphism or even isomorphism, it is about mapping. Mapping means that we are talking about the two groups which may have completely different composition, completely different elements, but we are going to discuss about the mapping of this. Yeah. So this group, let's say, will have element, let's say A, B, C, D. And okay, I mean, just for the sake of convenience, I'm writing these A prime, B prime, C prime, D prime. It is as if basically I have a map which is existing, which will take an element of this group G to the element of the group G prime. So I can think about phi A, phi B, phi C as the element, as the map which will take me from group G to group G prime. This is what we are going to discuss about. So phi from G star to G prime composition. This is just to show that it can be any binary operation in the other one, is a group homomorphism. So now the definition, if phi A star B, remember this star is the operation in my first group, is equal to phi A dot phi B. This is interesting. Yeah, what does this tell us? Even though the relation looks very simple, it is telling you that if you are having two elements in our group G and you compose them, let's say A star B. So this will be sort of a new element which is coming, right? Let's say this element comes out to be F. So A star B, if this comes out to be F, then it is going to map to an element here in another group, which will be F prime, which is nothing but the phi A composition with phi B. So if you look into this relation, the relation is saying something, I mean, it is a very important constraint that if you are going to take a composition A star B in one group and take the map of that phi, then it will take you to an element which is nothing but the composition of the two elements phi A and phi B, which were the images of your original A and B, and that composition will give you exactly this F prime. So phi is defined as group homomorphism. This map is defined as group homomorphism if this relation phi A star B holds true, that is equal to phi A dot phi B. I am not restricting at this point of time how many elements can be mapped to single element, whether it is one-to-one mapping, whether it is on to bijective, surjective. I'm not saying anything about that. I'm saying as long as there exists a map phi which will take phi A star B to phi A dot phi B, we say that phi is a group homomorphism. Again, sounds like an abstract thing. So we will have to do an example and only then we will understand it. Yeah. So some of the simple repercussion is something like this. So phi A is equal to phi B is possible even if A is not equal to B. What does that tell you? So even if elements are different in my first group, which is left side G, but the mapping results in the same phi A and phi B. Yeah. So what kind of mapping is this? Two distinct elements mapped onto the same element. No, you have done the mapping, right? Okay, I'll not ask question on that, but okay, I'll discuss it. Let's take an example and then see how it works in real life.
Many one, sir.
Many one, yeah, but many one is said in some set theoretic language, right? I mean, set theory language.
So on to.
Is it on to? Yeah, I am just asking. I do not want to give an answer to this question because that means that you are not going to go back and look at this. See, it has nothing to do right now with our homomorphism in the group theory. But in general, whenever you have this mapping defined, remember the two mappings which you have defined to begin with, injective, surjective, and then you say a bijective map. So those, please do not forget about that. I mean, I understand that many of the things we tend to forget because it is very difficult to remember everything. But this is a concept in the maps which is very important for you. So just keep it with you. What we are going to do in the group homomorphism is what I am going to explain in an example. Wherever you get stuck, just ask me a question there. Okay. So let me take a simple example. So G star cross. So I'm not even changing the operations between the two, even though I can, but I'm not changing, right? And I'm saying I am taking a group 1 minus 1, I minus I under the complex multiplication, and G prime I am taking this. Yeah, so I have this guy G, and then I have this G star. Now I can think about a map now of phi, which will take element of my first group and gives me element of the second group. So let me just give you a map. Phi 1 is equal to 1. Phi minus 1 is equal to 1. Phi I is equal to minus 1. And phi minus I is equal to minus 1. So I just constructed a map where 1 minus 1 gives you, so of G, gives you E of G prime, and I and minus I gives you minus 1. And you will say, why did you construct this? Okay, I will construct something else also after this one. But I just want to see if phi A star B is equal to phi A dot phi B under all the cases. And in this particular example, this dot is same on both the sides. In some other example, it can be different. So let's just try to see. Okay. Question is phi a group homomorphism? So let's just try to answer this. First, what do we have to do? Phi 1 star minus 1. First possibility. So what is phi 1 star minus 1?
Phi minus
LH.
1.
So this will be phi of minus 1. Yeah, because 1 star minus 1 is equal to minus 1. And what is phi of minus 1 in this map?
1.
Equal to 1. Let's look into the right hand side. Phi 1 star, since in this case it is same, phi minus 1. This is RHS. What is the result? Phi 1 star phi minus 1. What is phi 1?
1.
1. What is phi minus 1?
1.
1. What is the result of 1 cross 1?
1.
1. So is the LHS same as the RHS?
Yes, it's
Yes,
all
for this element. Now do that for me, for other elements also. So let's say I into minus I, phi. So let's just consider this LHS. Sorry, this is LHS. What will be this I star minus I? I star minus I.
1, sir.
1.
Plus or minus?
Plus.
Plus.
Plus. Great. So phi 1 is equal to, mapping is 1.
1.
What about the RHS? Now, phi I star phi minus I. Phi I star minus I. Phi I, what is that?
1.
Minus 1.
Minus
And
1,
what
sir.
is phi minus I?
Minus 1.
1. What will be the result of this?
1.
1. So is the LHS same as RHS?
Yes, sir.
Yes. Please do it for rest of the two elements at least. Since it's an abelian group, so let's not worry about I into minus I or minus I into I. But let's just do it for two more elements and tell me whether you find that the relation holds true for all the elements for this mapping, where two of these is mapped in this. Please do that.
Yes, sir.
Yes. So what is the way to figure out if it is a group homomorphism for this structure? It's simple. It is a structure in which phi A star B is equal to phi A times phi B or star phi B. What kind of group homomorphism it is? Now that question is generally answered. How many elements of group G is mapped to how many elements of group G prime? So two elements of group G. So answer is first yes. Okay, let me just write it down here. two elements of group G mapped onto one element of G prime is what we call as 2 to 1 homomorphism. There can be 3 to 1, there can be 1 to 1, there can be n to 1 homomorphism, in which we have to know about number of elements of G which are mapped to number of elements of G prime. So before 2 it is the number of elements of G. After 2 it is the number of elements of G prime. Okay. Now you may think that what I gave you as an example, it may look like that everything will be mapped like this. So let me just ask you, for example, let's say we have a question where we do exactly opposite. Let's do something like this. Now 1 and minus 1 map to minus 1 and I and minus I map to 1. Yeah. And I ask you what will be phi I into, let's say, 1. Okay. So if you want to create mapping, you are creating a second mapping. So this should be example 2. So in which phi 1 is mapped to minus 1, phi minus 1 is mapped to minus 1, phi I is mapped to 1, phi minus I is mapped to 1. So phi, what will be phi I cross 1 LHS? Let's just see. Phi I, which is what? Equal to? Phi I is equal to what? Look into this mapping. 1. So let's do the RHS also. Phi I cross phi 1. So what is phi I? 1. What is phi 1?
Minus 1.
Minus 1.
Minus 1. What will be the result?
Minus 1.
Minus 1. So even for a single element, if it is that the LHS is not equal to RHS, you do not have the group homomorphism. So the group homomorphism which was there in this previous example of mapping, where 1 and minus 1 were mapped to 1 and I and minus I were mapped to minus 1, that is not happening in the case of this particular, where 1 and minus 1 are mapped to minus 1 and I and minus I are mapped to 1. So it's not that all the time you will get the group homomorphism. It will be only for certain mappings where you are going to get it. So you can take example. I mean, you want to do a homework, for example, do a example 3. 1 and I map to, let's say, 1 and minus 1 and minus I map to minus 1. Do this question, for example, as a homework and see what result you will get. One thing which of course can be proven, but I am just going to write down for the group homomorphism is this one. Phi of this element E of G. So there exists this G, there exists this G prime, and this E is there. So I am calling this E, which is on the group G side, that identity element of G. This will always be mapped to the identity element of group G prime. It is mandatory. So that means that if you look into the mapping which I am constructing, if one of this group, number 1 of this group, is not mapped onto one of this group, then I am not creating the right mapping anyway for the group homomorphism. You can just take this as first exercise and you say, since 1 is not mapped onto 1, which is the identity element on both the sides, hence this cannot be group homomorphism. Not only this, there is another interesting property of this, which is inverse of the element, and you take the map of that, will always be equal to this guy for group homomorphism. Both of these properties can be proven, but I am not doing it. It is a very simple exercise. You can please check it. But these two are very important things which come out for group homomorphism. Identity element always map onto the identity element of the other group. And if there exists A, and of course correspondingly inverse of that, then if A maps to phi A, then A inverse will always map to phi A, as if you have taken an inverse on the right hand side. So these two conditions will have to be satisfied. Even if one of these does not meet, That means it is not a group homomorphism. And from where it is coming? It is coming from the definition of this. A cross B is equal to phi A dot phi B. So at this point of time, I will pause, I will stop. I will continue with this group homomorphism and group isomorphism in tomorrow's class. But question, if you want to have, please ask.
Sir, inverse is also true, no?
Yeah, I mean, it is one and the same thing, right? Its inverse means what? You are always mapping from left to right, right?
Yes, I got
Yeah.
it.
Till you reach to isomorphism, you haven't defined something. Okay, it is only for you and others if they can understand. I haven't defined something called phi inverse. Since there is no phi inverse, so you are always mapping from left hand side to right hand side. So there is no mapping which you are doing backward. You do not even know whether phi inverse exists or not, right? In this case. So group homomorphism, there goes mapping only from LHS to RHS. So identity element will always be mapped to identity element. And two groups do not need to be same in any respect. That is the bigger thing for this. And I wanted to just end with this question. Those of you who are interested, there is this group Z plus, which is now for me integer addition. Remember, this was a group which we had, and G prime, which is a group 1 minus 1 under multiplication, the one which we just had. And I create a map phi n, which is such that elements from group G are mapped to elements of G prime whenever phi n, where n is an integer, it is plus 1 if n being even. So whenever it is a positive integer, I will map to plus 1, and whenever it is negative integer, I will map it to minus 1. Question, is phi a group homomorphism? So now you see that there are countably infinite elements in our left hand side, whereas there are only 2 elements on the right hand side. You can see that composition is addition on the left hand side, whereas the composition is multiplication on the right hand side. So this is an example where we, of course, utilize the full power of this group homomorphism. And those of you who are thinking, okay, I mean, this may be group homomorphism, they can think about doing something else also. Second, opposite, minus 1 if n being odd, okay, plus 1 if n being odd, and minus 1 if n being even. Yeah, they can even take this example, second one also. Do that, and tomorrow we will discuss it. Fine. It's already beyond 3, and you must be exhausted by this time. My group is not exhausted, but we are.
Just a quick question.
Yes, quick question. Yeah, go ahead.
Sir, phi n is equal to plus 1 minus 1. ये क्या है मतलब solve नहीं है?
Oh, अच्छा. Z का group. Yeah, I can. Good. What is the number of elements in Z? जरा सा number बताओ मुझे. So 0, 1, 2, 3, minus 1, minus 2, right? ठीक है? यही ग्रुप हुआ ना ये? लेफ्ट वाला.
Yes.
और राइट हैंड साइड में तो 2 ही एलिमेंट है. तो जब मुझे मैपिंग बनानी है तो मुझे तो लेफ्ट हैंड साइड के सारे एलिमेंट्स को मैप करना है राइट हैंड साइड में, है ना. तो मैंने एक सिंपल नोटेशन निकाल दिया. जब भी n इवन आ रहे हैं आपके इंटीजर्स, हाँ, सो -2, 0, 2, 4, 6, so on and so forth, सारे के सारे. Yeah, then it is mapped to first element of the second group. And जब भी odd integers आ रहे हैं 1, 3, 5, 7, 8, so -1, -3, so on. I am mapping them to n being -1. तो मुझे सारे एलिमेंट्स में, मेरे पास बहुत एलिमेंट्स थे, पर मैंने उनको जी प्राइम के 2 एलिमेंट्स में, जहां पे कि केवल +1 और -1 था. तो आप ये सोच सकते हो इवन नंबर्स आर मैप्ड टू दिस, ऑड नंबर्स आर मैप्ड टू -1. So it is almost like infinity to 1, right? Infinite numbers are mapped to only one number.
Yes,
Got the
it.
answer? Yeah. So this n is an integer which reflects the group elements of left hand side. Yeah. Good question. Anybody else? Yeah, unless we do examples of homomorphism, we are unable to understand. Yes, please go ahead. Somebody is going to ask question. Yeah, please go ahead. Okay, no. Yeah, it's very difficult to ask question at 3 p.m. when everything is done. I mean, mind is exhausted. Okay, guys, let's meet tomorrow with some fresh air.